Hello, my name is Adam Gripton. I'm an assistant professor for the Centre for Sustainable Road Freight at Heriot-Watt University in Edinburgh, and my talk for the conference is called Improving the Conditioning of ERS Feasibility Studies through a Preferential Routing Algorithm. To get some context as to where the research I'll present fits into the wider debate around road freight and decarbonisation, let's first set the scene. It's beyond debate now that radical decarbonisation of road vehicles needs to happen in order to stand any chance of hitting net zero climate targets. Although long-haul logistics journeys are of critical importance to national infrastructure, they are responsible for a significant proportion of overall transport emissions. And as things stand, long-distance logistics still needs to up its game if the transport sector is to achieve its own emissions targets. At present, long-distance truck movements are still overwhelmingly dependent on diesel, in a manner that increasingly cannot be said of short-haul logistics and private cars, which are beginning to transition towards battery electric power. This reliance on HGV diesel is due to several reasons, including the mature, dense and well-serviced network of HGV fueling stations in and around the UK's strategic road network, the irregular coverage and unreliability of existing locations to provide rapid electric charging to larger vehicles, and the fact that hydrogen infrastructure is almost non-existent within UK road freight. So unlike light goods vehicles such as urban delivery vans, battery power alone is often not sufficient to cover long-haul use cases for two main reasons. The first is the higher energy usage of HGVs compared to vans due to the speed and the size of the HGV, but also the energy density of onboard batteries compared to diesel and the price. At a rough estimate, 10 tons of a typical HGV's available payload would be taken up with a battery capable of delivering the same 1,000-kilometre range as a 300-litre tank of diesel, and such a battery could easily cost £250,000 at current prices, whereas the smaller battery needed by the light goods operator may present much less significant issues. The second reason is the typical journey range of an HGV, in particular between its returns to its home depot, in contrast with LGVs that usually return home every evening, with electric LGVs often using such a return to take a charge overnight. Quite commonly, HGVs travel over 1,000 kilometres between depot returns, with the whole route sometimes taking days to complete, a practice known as tramping. This pattern of logistics, coupled with the sparseness of charging opportunities on the strategic road network when compared to urban areas, causes an issue when balancing HGV battery size with the desired service levels. As a result of some of these potential issues with large battery HGVs, it's reasonable to ask whether alternative charge-on-the-move strategies could assist in reducing the typical battery size requirement by providing consistent power along the road itself. Some configurations currently being tested in Germany and Sweden include an overhead catenary system similar to that of electric railways, and a charge-in-road system where the charge is drawn from a dedicated rail within the roadway. Such systems are referred to as electric road systems, or ERS for short. Regardless of which form it takes, the electric road system has the potential to significantly reduce the size of battery that an HGV requires for long journeys on major strategic roads, both by providing the vehicle's motive power as well as allowing it to charge the backup battery while travelling. As part of the Centre's studies, 3 potential UK configurations of ERS have been identified, from a light configuration covering just the busiest trunk routes, to a heavy configuration that connects most urban areas within Great Britain. Each configuration can be tested against a set of long-haul logistics journeys to establish the effect they would have on the range of battery sizes required, by using the assumption that the stretches of the journey powered by the ERS would allow for both motive power and simultaneous battery charging. For example, our studies have shown that deployment of even the light network, measuring 5,500 lane kilometers, can have a very significant reductive impact on battery size requirements. The problem is that due to the agnostic nature of the route planning engine, The quickest route chosen by a vehicle will not necessarily be the most effective route to choose in the context of an ERS and battery efficiency. Where several alternative routes are available, the routing engine will always pick a route predicted to be quicker, even if large stretches of the route take the vehicle off the ERS and therefore reduce the ability to operate the route on a smaller battery. Here we see an example of such a journey between Swindon and Newton Aycliffe in County Durham. If route choice is selected purely based on journey time, then a route through the Cotswold Hills and Warwickshire is predicted, crossing the M6 at Coventry and only joining with the ERS network at Leicester. This is clearly a suboptimal choice if battery size is also to be minimised, with visually intuitive routes via the M4, M5 and even the M25 presenting themselves as options. This motivates the design of an alternative routing system that can consider the network of ERS-enabled roads and make a value judgment on whether it is worthwhile to preferentially route via the ERS network or whether to maintain the original plan. Such questions could also be pertinent when considering an HGV's battery being low on charge after serving a customer. It may be quicker to route preferentially towards ERS-enabled roads than wait to charge to full before setting off. R works on a software solution that can find alternative routings based on a known ERS configuration we provided, and which can return several route alternatives to illustrate the trade-offs that can be made between battery requirements and speed. Our approach begins by considering the functionality of the open source Graph-Hopper routing engine, specifically version 0.13, which was posted to GitHub in 2019. We use this because this was the last version to support an offline routing ecosystem that can take locally stored snapshots of OpenStreetMap data as input. The aims of the software project are twofold. The first objective was to make an altered copy of the Graph-Hopper engine and adapt it to allow us to specify in the request to what extent the routing should consider the location of ERS routes when performing its route finding. At one extreme, this parameter will route as if ERS routes are of no benefit to the travel time. At the other extreme, this parameter will route as if ERS routes can be traversed instantaneously with only the travel time of connecting roads considered. The second objective is to alter the Graph-Hopper map building engine so that a map of ERS routes can be read in from the shapefile definitions provided and attached to the road properties within the map definition. This will conditionally mark a set of routes as being ERS enabled, using the same data structure that Graph-Hopper uses for weighting routes in other ways, such as maximum speed, road quality, and so on. An example set of road link properties from OpenStreetMap is displayed here. We'll give some details here about the software changes that were necessary before moving on to implementation details. To support the objectives as shown here, the software changes required 2 existing Graph-Hopper classes to be duplicated and altered, and 4 extra helper classes to be added to the Graph-Hopper computational engine. We'll start here with the duplicated classes. First, the main Graph-Hopper class itself had to be altered in order to specify a new replacement interface that allowed the road network graph to be edited at development time, allowing the analyst to set up scenarios that modify the road network by either light, medium, or heavy ERS networks, or indeed any other arrangement of ERS, without needing to hard code this capability into the algorithm itself. To support this, we also needed to allow the ERS weighting parameter to be passed through in order to tell the graph solver how to deal with ERS-enabled road links. To ensure backwards compatibility, this also necessitated including support for a new type of solver, which we'll describe in the next slide. Additionally, the change graph helper class needed to be modified in order to allow the analyst to read and write ERS flags to any road links of their choice, again subsequently allowing these to be read in by the graph solver. In addition to the duplication and alteration of those 2 base classes, we also had to write 4 classes from scratch. The first of these is iChangeable Hopper, which the main Graph-Hopper object now points to instead of its usual API. It duplicated the base functionality, but now allows changes to the road network graph to be made by the analyst. The second added class is the fastest ERS weighting graph objective function that can now be selected by the solver at runtime. This is the core of the new computational method, allowing the provision of the new extra parameter E to specify the ERS weighting. This class can detect whether the road link in question is ERS enabled and returns the usual time-based weighting x if it's not part of the ERS, otherwise returning e times x. The effect of this is that when e is set to 0, the ERS is essentially free, and when e is set to 1, it reproduces the default non-ERS behavior, with the analyst, of course, now able to pick any intermediate floating point value of e between these two extremes. The third added class is a replacement for the default car flag encoder. This ensures that the logical bit that represents whether a road link is ERS enabled or not is registered within the encoding of the road within the network. The final added class is a replacement for a factory object, which now returns instances of the ERS type encoder that we just mentioned. This ensures that the weighting parameter e can be passed through for further computation. It's also worth reflecting that considerable luck was involved in writing this architecture, as the default graph hopper encoding takes up 31 of the 32 bits of memory that are permitted for defining each road link, thereby leaving only just enough space for our final bit to be included in the definition to signify whether the road link is ERS enabled or not. In order to deploy the new architecture within a logistics analysis, the user must first use the new type of encoder factory that we've written, taking the opportunity at this point to specify E between 0 and 1. They must also use the new altered graph hopper object and point it at that encoder factory before loading the offline road network in the usual way. After loading in the network, the user must mark the graph hopper map with their chosen set of ERS roads that correspond to the shapefiles provided in the definition. We've written a helper function to assist in this when the ERS definition is given as a KML format. GraphHopper's internal routines are then utilized to snap any local discrepancies to its own definition of the road network. So we now return to our Swindon example from earlier. By varying the parameter used for ERS weighting, the modified GraphHopper has now provided 3 further alternatives to the original route, as shown in blue. We'll call the blue route option 1. Due to the long uninterrupted stretch of the journey away from the ERS, this route is predicted to require a 323 kWh battery to complete. Option 2 in green and yellow, the first of the newly discovered options, exhibits a slight preference for the ERS and already has a dramatic effect on the battery requirements. As the long stretch across the hills has now been replaced by 2 shorter stretches away from the ERS, this route uses the fact that the ERS can charge on the move, allowing a routing via Gloucester and then the M5 and M42. By the time this route leaves the ERS again near Birmingham, the battery is reset to full, and the second stretch of a similar length to the first does not cause an issue for the 110 kWh battery predicted to be required. This route option only takes a few minutes longer than the original identified option. Option 3 is green on the diagram and has a heavier preference for the ERS, but at a significant time cost and without having a really appreciable effect on battery size. This is as it still crosses to Gloucester but then stays on the ERS for the remainder of the journey, routing via the M62. As the 2 unwired stretches of the yellow option 2 route were far apart and of roughly similar size, we see that the battery size savings are minimal. Option 4 is pink on the diagram and is a good example of a very heavy preference for the ERS. This route takes nearly a full hour longer than the original journey, but its battery requirements are minimal, requiring only 20 kWh of available battery to complete. This route stays on the ERS for almost its entire length, taking a circuitous route via the M25 London Orbital. A good example of where such a route may be adopted in practice is if an HGV with an otherwise large battery had left the origin point without much remaining charge and chose to use the ERS as a mobile charging facility, in preference to stopping at a static charger. So let's see the experiment that produced the 4 routes from the previous slide. To create these results, the routing engine was run several times over a set of incremental values of E between 0 and 1. Immediately evident is that these 4 routes each show themselves to be the most optimal route for a certain interval of the parameter E. The graph on the left shows the total distance of each route, and the time graph would look very similar. Option 4, the route that sends the HGV via London, is clearly the longest journey, with option 1 across the Cotswolds being the shortest. In the graph of maximum battery depletion, we can see visually how much of a difference such alternative routings can make if they're chosen, with option 4 requiring a dramatically smaller and option 1 equally dramatically larger battery to complete than either of the more average options 2 or 3. Depending on our cost model for the value of time or distance travelled, alongside the truck's current battery status where applicable, the scheduler would need to make a judgment of which of these routes to take in practice. But these results show that such a decision can be supported through a selection of calculated routes that have taken into account the ERS topology. A natural question that could be asked of this method is whether we can interpret the parameter E in terms of the value of time saved. If such a relation can be identified, this would allow the parameter to be chosen adaptively based on the scenario that an HGV finds itself in, rather than needing to be run several times over a fine grid of possible values each time. This would make significant savings in computational time. Although we've not yet identified a fully operationalizable answer to this question, one starting point is for the simple case where an entirely ERS route would be chosen over an entirely non-ERS route. This simplification admits a closed form solution, which is that choosing a value for E will mean we can tolerate the travel time being 1 minus E over E longer than if the original non-calibrated route had been chosen, and therefore we can choose the best value for E based on, for example, patterns of driver breaks. This table gives a few common cases of where this could be used. For example, E equals 0.8 means that a 25% longer route entirely on ERS can be tolerated, which may be useful, say, at a half-charge state, whereas an E of 0.5 accepts double the travel time for an ERS route over a non-ERS route. Again, these examples are based on the candidate route being wholly ERS enabled, with the base route being wholly off the ERS. In the example we've identified before, this would be equivalent to routing between the origin point and the location around Leicester where the original route joined the ERS. So to recap, in this presentation we've shown that it is possible to use the offline version of the Grasshopper routing engine and modify it in a way that it can produce alternative routings that are informed by the topology of a candidate electric road system arrangement that is provided to it, allowing the analyst to provide a sliding scale of weightings ranging between ignoring the ERS entirely and considering ERS roads as zero cost. We've also shown how, by varying this weighting parameter, different routings can present themselves as the optimized objective of this alternative routing engine, which could provide vital information from a logistics controller to optionally route via a longer route if the battery take is less than that of the original. This has applications both in assigning HGVs with smaller onboard batteries to some routes, but also in the case of larger battery HGVs that may be running near empty. Finally, we've shown that the calibration parameter does have a real-world interpretation, at least in the simple case where an entirely ERS route is being considered as an option to an entirely non-ERS route, and we hope to generalize this interpretation in future to allow scenario-specific adaptive values of this parameter to be automatically calculated, which would save computational time and reduce the need for subjective judgment in route choice. Thank you for your attention. I'd be pleased to answer any questions you may have. My email is also on screen should you prefer to contact me in this way.